Okay, welcome to lecture 6.6. Okay, so we're now on Grossclitz Levitt Snyder adjusted interest group scores. Okay, here are the assumptions and the definitions that we make in our paper. Okay, first, we define YIT equals the nominal score of legislator I in year T. Okay. Now it turns out we're going to also make interchamber comparisons. And so we have to also make scaling adjustments from chamber to chamber. And so in the actual paper, we put a C, so which chamber it is. And that C was either House or Senate. Okay. I'm going to ignore that for the moment. Okay. It makes it a little more complicated than it needs to be. The key is we're going to have legislator I. He has a nominal score. We call it YIT. And this is just the score that the interest group reports, like the ADA reports. So in year T, person I, okay, that's YIT. Now we are going to define YIT equals the adjusted score. And by the way, when we first wrote the paper, we called it nominal scores and real scores, like prices and macro. So the nominal GDP and real GDP. But I think the editors told us they like adjusted better. So we call YIT the adjusted score. So that it's gonna be like like you do in macro. You have a price index. You take the consumer price index. You divide the nominal wage or nominal GDP by the price index. That gives you the real GDP. And from there, you can make comparisons from year to year. Did the real GDP increase from year to year? Now, the way we're going to do that, so with macro CPI, all you do is just divide by the consumer price index. Okay, we're going to do something a little different. We're going to assume that the scales are a little more complicated. So with prices, you have that CPI that like stretches the scale. It blows up the scale or shrinks it depending on whether the CPI is greater than or less than 1. We're going to assume that they also can shift. So the scales can shift and then possibly shrink or stretch. And so we're going to assume that it's like temperature. So it's like converting Fahrenheit to Celsius, or back the other way. You have the Fahrenheit. When you convert Fahrenheit to Celsius, I think what you do is you take the Fahrenheit score, subtract 32, and then multiply by 5/9. I think I got that right. Anyway, what we're going to assume is we assume that YIT, the adjusted score, equals YIT minus AT. Now, AT is going to be a parameter that we estimate, divided by B of T. So how would this be? So if YIT was the Fahrenheit temperature and we're converting to Celsius, AT would be 32, BT would be 9/5. Okay. All right. Now, next, we're going to have another parameter, XI. Okay, I'm going to be a little vague about what it's defined to be. Weighted average of adjusted scores. Okay, so for person I, XI is the weighted average of adjusted scores. Now, it turns out XI, we apologize for this. Now, usually, XI represents data, But here in our paper, xi is a parameter to estimate. It's something like a fixed effect for each person. Okay, so we have an AT, BT, and then an XI. So if we have 40 years worth of data, we're going to have 40 ATs, 40 BTs, and then we're going to have an XI for every member who served. Now it turns out, say we're only looking at the House. If every member served in every year, that is, there was no turnover, there would be 435 XIs. Now it turns out only something like 80 to 90% of them return. So, the 20 years, I think the total number of XIs would be something like double 435. So, okay. So, anyway, the key is XI, remember that is a parameter. Okay. Now, um, okay. Now, what we say it with no randomness. Okay, so no error, and so there's no idiosyncratic changes in I's preferences. And so what that would mean is the only reason this YIT would change is because the scales change. Okay, so that would mean the Y hat IT would be the same every year. Okay, if that were true, what we would have is XI equals Y hat IT for all T. So that's sign and real analysis logic for all T. That means for every year that YIT is just a constant XI. Okay. If that were true, then in every year, so I'm going to substitute XI for here, that Y hat IT XI equals Y IT minus AT divided by BT, which implies just do some arithmetic or algebra maybe. YIT equals AT plus BT times XI. So multiply each side by BT XI, and then just subtract AT from both sides. That will get you that. Okay. With randomness, we're going to assume there's an error term. YIT equals AT plus BT XI plus epsilon I sub t. Okay, where that is an error term, and we're going to assume that is distributed normal 0 sigma squared. Okay, so that is where we're going. Okay. So the PDF of epsilon IT. So it's let's see. So remember, we assume that it's not standard normal, but it's normal with standard deviation equal to sigma squared. Now it turns out that the PDF f of epsilon IT. So we just take the CDF and take the derivative. You can prove this. It's just a couple steps, but it must equal 1 over sigma times little phi of, call it epsilon IT divided by sigma. Okay, where little phi is just the standard, the PDF of the standard normal. So that actually equals, it's going to be 1 over square root of 2 pi e to the negative, whatever's in parentheses, so epsilon IT divided by sigma squared divided by 2. Okay. Okay, that's what that means. You just stick in where normally we'd put z, you just stick in whatever's in parentheses. Okay. Now, the key is, though, you got to multiply that 1 over sigma times that standard standard normal PDF. Okay. Once you do that, our data is all the, would say we did this for the ADA. We could do it for any interest group, but say we do it for the ADA. So suppose that we restricted only to the house for the moment. We looked, and I'll tell you this, we had data, almost certain this was right. Data went from 1947 to 1996. So it's 50 years worth of data. The likelihood function is just going to be L of I'll put it in braces, AT, so it means the set of ATs, 50 of them, set of BTs, the set of XIs is going to be, let's see, everyone probably served on average, if it was 10 years, it's going to be 5 times 435, something like 3,000 XIs. And then sigma. So the likelihood of all those parameters, remember ATs, BTs, and the XIs, those are all parameters, that equals just big pi over all the i's. So I equals something like 1 to 3,000, however many different members there are. Then also take the product over all the years, so 1947 to 1996, and then you just put in the likelihood function. So far all of our variables have been discrete variables, and so we talk about the probability of observing something. Well, it's not quite correct to say we're going to see, because we assume that this variable is continuous, and we're going to say the probability of it being exactly this value. And so if it's a continuous random variable, we say it's 0. The probability that epsilon IT equals 1.67, well, that's 0. But when we take an approximate, or we take the limit as delta approaches 0, that the limit, the probability that epsilon IT was in delta of 1.67, and then let delta approach 0, it's always going to be a constant times this. So think of it, it's like we're saying the probability epsilon IT equals whatever value we're imposing here. So, and what we're imposing is going to be the actual score that we observe minus that AT minus BT and so on. Okay. More specific, it's going to look like this. Phi, 1 over sigma divided by phi times, we observe their data. It's like our dependent variable, YIT. We observe it, that person I in year T got a YIT score minus AT. That's our parameter. That's BTXI, all divided by sigma. Okay, so it's like we're essentially saying the probability that error term equals exactly YIT minus AT minus BT times XI. Okay, that's how we're constructing the likelihood function. Okay, And once we do that, all we got to do is maximize this, find the ATs, BTs, and XIs and sigma that maximize it, and then once we've done that, we've estimated all the shift parameters, stretch parameters. Shift parameters are the ATs, stretch parameters are the BTs. And then we also have sigmas, and then the XIs. That's what we're calling the weighted adjusted factor. It's like a fixed effect factor for person I. Okay, and then we would have estimates. Okay, let me show you. And then eventually, what we're going to do, we're going to define the real score. It's like the predicted nominal score. We just define that as AT hat minus BT hat times XI hat. Is that right? YT minus AT times. No, that's not right. That's not right. The YIT hat. So if you recall, I said that where there's no error, YIT equals AT plus BT XI. XI. Well, and then if there are also no error, that XI is always going to be that Y hat IT is always going to be the same. So we can just manipulate that equation, and so what we're going to get is we define YT hat, the adjusted score, just equals YIT minus AT divided by BT. Actually, hats for all the parameter estimates. Okay, so once we get the estimates of the ATs and BTs, we're going to say these are our conversion factors, and they say these are our shift parameter that adjusts that the amount the scale is shifted in year T. BT is the stretch factor, the amount the scale is stretched in year T. We're going to use those as like the 32 9/5 that you have in Fahrenheit to Celsius to convert nominal scores to what we call a real score. Okay, so we're defining real scores to be that. Okay, so that's what we do. That's how we get estimates. That's how we get parameters that allow us to shift the scales. One issue. Let me talk about whether all of these parameters are identified. Okay, turns out they're not. So let me discuss that in the next segment. Okay, I'll see you there.